Okay, so we'll start. Today we'll have Kewen from IIS. We can talk on locally sampleable uniform symmetries.
Okay, yeah. Is my voice okay? Okay, so yeah, I'm Kevin from IIS, and today I'm going to talk about this joint work with Daniel King and Anthony Osuni from UCSD. So the plan of this talk is to first describe the problem, give some background information about it, and then I will describe our results. And after that, I will mention some open problems that we cannot solve, but are very interesting. And in the end, I will talk about the proofs. Yeah. Oh, by the way, feel free to ask me any question during the talk. I'm happy to clarify. Wait, why it doesn't work now? Okay, so the key question we try to understand is this sentence: what distributions can a shallow circuit produce? And I will go term by term, explaining what this means. So the first thing is a circuit. Like, what is a circuit? The circuit will be the like standard Boolean circuit where you have Boolean operations here, like and or negation, and we assume the gates are taking like constant number of inputs. So it's a constant depth circuit with bounded fan in and unbounded fan out. So the input will be binary bits, and the output is not just one bit, but many bits. So here is like one case. And the shallow means the circuit itself is shallow. Like for any path from input to output, it is short. You can think of it as a constant or a very slowly growing function with respect to the input length. So this means this is the definition of shallow. So if you learned like complexity theory, especially like circuit complexity, you will see that this is NC0 circuit. This just like multi-output NC0 circuits are very fundamental and basic circuit class in theoretical computer science. On the other hand, even though I phrase the question in terms of circuit, but this is more general than circuit itself. For example, if you like polynomials, you can think of this as like evaluating some polynomials. Like every output bit, for example, B1 is going to depend on some number of input bits, and you can expand it in terms of polynomial. Like what is a polynomial you evaluate to produce B1, and similarly for B2 and B3. And because this is a shallow circuit, and think of this shallow means like constant, then this polynomial is going to only depend on constant number of input bits, and this is a constant degree polynomial. So you can view it in that way, or if you like dissymmetry, then you can express the computation of each output bit in terms of dissymmetry. Like you read some input bit, and depending on whether it's 0 or 1, you read some other input bit and go on. And because this is shallow circuits, this dissymmetry is going to be a small size, in particular constant size. And also, you may intuitively view this as some kind of weakly correlated computation, because every output bit depends only on constant number of input bits. Then intuitively, they cannot generate some like long-range correlation among many of them. So this is some kind of weakly correlated computation. And there are some like other ways to view it. So even though I phrased this question in terms of circuits, like this is like more general than circuit itself. Okay, so that is circuits. What about distribution? Like, what is a distribution here? I fixed a standard, like a static circuit, and the distribution is we fix the circuit and we consider the input to be random, in particular unbiased coins. And then for any particular input, the circuit will produce a fixed output. And because the input is random, the output is going to have a distribution. Okay. And the output distribution will be the distribution that we care about. And I will fix it to be like n bits, although I don't fix the input length. Like you should think of the input as unbounded, and I just care about the n-bit output of the circuit. So I would use D to denote this distribution, which is a distribution over the Boolean hypercube, 0, 1 to the n. And the question is too arbitrary, like too generic. Like, for example, if I want to describe a distribution to you, like how can I efficiently describe to you? Like, this is in itself a very hard problem. So we will have to put some constraints on the distribution that I want to understand. In particular, we want to understand uniform symmetric distribution. And for such kind of distributions, it's first a natural object to study, and also I will mention like why do we care about this. So the uniform means it's a uniform distribution. Every distribution has its supports, like some value, like some ambit string that it's likely to output. And uniform distribution means you just pick uniformly random from it. And symmetric means the support of the distribution is symmetric. That is, if you can output string x, then any permutation of the x will be outputted as well. So this means it's symmetric. And uniform symmetric means it's both uniform and symmetric. Okay. And here are some examples and non-examples. The first one is the uniform distribution over everything, like all ambit string. It is uniform and symmetric by its definition. The second one is assert bias distribution. Means every bit is like independent, and it has a third probability outputting 1 and 2/3 probability outputting 0. And this is a symmetric distribution because every binary string is going to be outputted, but it's not uniform. Like you will have more probability outputting 0 than 1. The third one is we fix the Hamming weight to be n/2. Like the string is going to have n/2 ones, and we take the uniform distribution over it. So this is uniform and symmetric. And the last one is a point distribution. And point distribution is always uniform distribution. And I also fix this point distribution to be like all 0 string, which means it's also symmetric because any permutation of all zeros is still all 0. So these are like simple examples, but there are more examples. Okay, so why do we care about this problem? And in particular, why do we like impose this uniform and symmetric condition on it? So first motivation will be this seems to be a natural problem to study on its own. Especially in theoretical computer science, we want to understand the power of different computational model. Like given a computational model, we want to understand what kind of computational task it can execute. And this is similar question. So we want to understand what kind of task can shallow circuits do. Well, in terms of computation, this seems a trivial like answer because shallow circuits means every output bit depends on constant number of input bits. Then, well, it cannot generate hard it cannot compute hard functions. In particular, for the parity function, so you take m x1, x2 up to xm-1, and you want to output the parity of them. This cannot be computed using with shallow circuits. The reason is fairly simple because the output depends on all input bits. And shallow circuits cannot aggregate values from all the input bits. In fact, this is not only not in NC0, it's not even in AC0 if you know the definition. But for NC0 we care about, there is a short proof for that. On the other hand, we can study the sampling problem, like the sampling power of shallow circuits, and the distribution we want to study is naturally induced by this computational task. So we want to sample this distribution. The first m-1 bits are unbiased, independent bits, and the last one is going to be the parity of the first m-1. So this, you can see, is a natural distribution to study given the computational task. And by writing it in this way, you can view a direct way to sample from this distribution. That is, you first sample m-1 unbiased coin, and then compute this function and put the evaluation value as the last output bit. So this is a direct computation to sampling reduction. However, as I mentioned, this computational task is not doable in shallow circuit model, like in NC0. So this approach doesn't work. So can we produce such distribution? It turns out we can do that. And this is achieved by like understanding the distribution itself. So we can take a look at this distribution and forget about the computational task, defining it. So what is this distribution after all? So this distribution is actually producing a uniform string of even Hamming weight. Why it's even? Well, because the first n-1 bits can have like arbitrary parity, but then the last one is going to cancel that. Okay, and why it's uniform? Well, the first n-1 bits are unbiased and uniform. So this string is also uniform. So this is the distribution we want to generate. And to generate such distribution, we have a better approach than directly computing parity function. This is, we can sample like n bits, y1, y2 up to yn, and take the XOR of the neighboring bits. Like the first output bit will be y1 XOR y2, the second bit will be y2 XOR y3, and the last one will be yn XOR y1, that it cycles back. And you can see this is going to produce an even string because every yi appears twice. And if you compute the Hamming weight, it will cancel modulo 2. And why it's uniform? Well, it's because like these yi's are uniform. So this is a way to produce the same distribution, but the benefit is every output bit depends only on 2 input bits, which is doable in shallow circuits. So it turns out the natural sampling task induced by this computational task is doable in shallow circuits, even though the computation task is hard. So this is a very interesting example, and it's natural to ask, are there any other examples, right? Like some computation task you cannot do in this shallow circuit model, but the natural distribution induced by this computation task is doable in the shallow circuit model. Like here, it's mode 2. Maybe you will want to understand mode 3 or mode 4, or if you want, you want to compute the exact Hamming weight, whether it's equal to n/2. Like all these kind of computation are not doable in shallow circuit, but can we generate the distribution induced by it? And it turns out the answer is no. So this is only miracle here happening, right? This function you cannot compute, but somehow the distribution you can generate. Okay, so this is the first motivation. And the second one comes from data structure lower bounds. In data structure lower bounds, we want to understand like how efficient can we construct our data structure. And here is a dictionary problem. Imagine you are given an n-bit string x that I promise you the Hamming weight is going to be 0 modulo 1, 2, 3. Here, 1, 2, 3 is some arbitrary number that I choose. It's not a prime. It's not a small number. And you should really think of it as a very general statement. And the goal is to store it as a data structure, H, of S bits. And we want to minimize S, as well as we want to achieve some fast retrieval procedure, which is if I want to know the ith bit of X, then I want to recover this value by reading a few number of coordinates from your data structure H. So the data structure needs to be compact and also efficient in providing like bitwise query. So given this problem, there are like a direct approach that maximizes the efficiency. We just store everything. If you give me X, I will like my data structure will just store this X as the data structure. And in this way, we will store n bits. And to recover the ith bit of X, we just read the ith bit of H, because that's just the ith bit of X. So this is maximally efficient. On the other hand, we can minimize the storage, ignoring the efficiency. And notice that I fix the Hamming weight of X to be 0 modulo 1, 2, 3. So there are roughly 2 to the n over 1, 2, 3 many possibility. So I can just use the data structure to store the index of my inputs, like which one of these 2 to the n over 1, 2, 3 possibilities did I get? In this way, the storage is roughly logarithm of 2 to the n over 1, 2, 3, and that's n minus 6. So you can save 6 bits in your storage. However, if you just want to know the ith bit of x, it seems still hard by reading few number of bits from your data structure, because this data structure is like compressing so many information that you cannot easily extract like the ith bit of x. So this is like the price to minimize the storage. But the question is, can we achieve both? Can we do some efficient recovery while save some storage? Like for example, I want to like, is there a better way to construct the data structure explicitly such that I can save 6 digits or maybe 3 digits and still read constant number of the bits to recover every bit of x? And it turns out the answer is no. And in particular, the result we get is either the recovery is not constant, you will need to read super constant number of bits from your data structure, or the data structure needs to store everything. And in which case, you only need to read 1 bit to recover xi. So this is proved by analyzing the question above. In particular, the connection is intuitively, assuming you have some very efficient data structure, then you can guess this data structure corresponding to each individual x and produce some distribution that is close to the uniform distribution over binary strings of weight 0 modulo 1, 2, 3. And by ruling out such distribution in shallow circuits, we rule out such data structure. Okay, so that is the second motivation from data structure. And the last one comes from classical versus quantum. So what we want to know whether quantum has advantage over classical computation. And in particular, the question here will be with respect to shallow circuits. So I defined the shallow circuit in terms of classical gates. You can also replace those gates with quantum gates. Informally, this is asking, can we use quantum shallow circuits to generate some distribution that is hard for any classical shallow circuit? I will not go into the detail of the definition of quantum shallow circuit, but you can see like this is an interesting question to ask, like whether whether quantum model has some advantage over the classical model. And in particular, this is generating distribution, so there is no input needed. Okay, like it's not a computational task. It's like input independent advantage. And it turns out the answer is yes, and this is unconditional. So we can use techniques developed to understanding that question to construct distribution and prove that it is hard for classical shallow circuits, and also that distribution is easy for quantum shallow circuits. Okay. So those are the like motivations and some related problems. And now let me go into the detail of what we proved. And to do that, I need to set up the notations formally. So let f be a mapping from m-bit binary string to m-bit output, and it will be a local function which captures the shallow circuit model. Here, local means every output bit depends on constant number of input bits. And let U to be the uniform random input, that is a uniform distribution over m bits input. And I use FU to denote the output distribution of F under uniform random input. So this FU will be the distribution we care about, we want to understand. And the question we ask is, when is this output distribution FU uniform and symmetric? Note that here I don't put any constraints on M versus N. So given such question, we can try to come up with uniform symmetric candidates that can be generated using local functions. The first one will be the constant like point distribution. And for point distributions, it needs to be like homogeneous, like every bit needs to be the same. So clearly this distribution is like generating the all zero string is doable for a local function. And you can also do all ones. And because you can do all 0 and all 1, you can do their mixture. So you can flip a coin, and if it's 0, you output all 0 string. If it's all 1, you output all 1 string. So every output bit will depend on this coin flip, but this is a local function. So these 3 distributions are generatable by local function, and they are uniform and symmetric. On the other hand, there are more complicated distributions that we already see, like from the parity example I showed you. That will generate the distribution of uniform even string, and this is the way to generate it. And because you can generate the uniform distribution over all even string, you can apply a shift to generate the distribution over all odd string. So every it's uniform over strings of Hamming weight an odd number. And because you can do the even, you can do the odd, you can do their mixture, which happens to be the uniform distribution over everything. So these are the 6 examples. I hope are like obvious enough to generate using constant number of using constant locality. Yes. Oh, so one way to do that is to flip a coin. And then if it's 0, you do the first one. If it's 1, you do the second one. Oh, you just like wire this choice bit to every output bit. And imagine you have 2 procedures, like one procedure generating the even string, one procedure to generate odd string. And you use this choice bit to decide which one to do. So every output bit will not only access to this choice bit, but also access to the computation that it will execute, like for the even and for the odd. And depending on this choice bit, you choose one of them. So this is like one way to do that. Although for this special distribution, you don't need to do that because you just wire every output bit, the ith output bit with the ith input bit, and you just output it. So like there are 2 ways to view this. Yeah, either way, it will be a local function output. Does this make sense? Any other question? Okay, so these are the 6 candidates that we see are uniform and symmetric and can be generated by this local function computation. However, this is not the only uniform symmetric distribution we can come up with, right? For example, I just want to output a binary string that has at most 10 ones. I want to fix the Hamming weight to be n over 2 and output a uniform one of it. Or I want to output a string that has like the number of ones is 0 modulo 3. So these are all valid uniform symmetric distribution, and there are more of them. Can we generate these distributions? And you can try, but it seems hard. And this is in fact a conjecture saying assuming n is sufficiently large with respect to the constant hidden in the constant locality, there are no other examples. Like these 6 distributions are the only examples you can generate using local function. And our contribution is to make this conjecture a theorem. So these are the 6 distributions you can generate. And like quantitatively, we can set D to be the locality. So every output bit depends on D input bits. And we still want to understand FU, which is output distribution. And we can do it in a robust version, like not just talking about exact computation, but allowing total variation distance. So assume the distribution, our output distribution is epsilon close to some uniform symmetric distribution. And this epsilon closeness is measured in total variation distance of 2 distributions. Then what we show is it is in fact order epsilon close to one of the following 6 distributions. So well, this theorem needs to assume n is sufficiently large depending on D. However, this constant is not is independent of D. Okay, so even approximately, these 6 candidates are the best you can do. You mean like the dependence on ND? Oh, this is one of the open questions I will mention soon. Yeah. Okay, so the takeaway here, before I mention the open problem, is we have 6 special distributions that are fairly easy to generate using local function. In particular, there are like 2 local, well, there are at most 2 local. Like each one of them can be computed very easily. I don't need arbitrary large constant. I just need constant that's as large as 2. However, even if you have larger constant, this is the best you can do. So to generate uniform and symmetric distribution, larger constant locality is the same as a locality of 2. Okay, so the summary here is we characterized all the uniform symmetric distributions that can be locally sampled, and there are 6 of them. And you may want to like drop this uniformity constraint. I just want to understand what kind of symmetric distribution you can generate, right? And this is a work in preparation, and we can do classification as well. So it will be almost a mixture of evens and odds and p-bias distribution. Here, the even will be like uniform distribution over even string. Odd is uniform distribution of odd string, and p-bias is like independent bits, and every bit has bias p. On the other hand, and also furthermore, this p needs to be a dyadic rational with constant denominator, and the mixing weight should be a dyadic rational with constant denominator. This is the classification result. Yeah. So if you can sample a symmetric distribution using local function, then your distribution is close to a mixture of these 3 special distributions where this additional constraint needs to be satisfied. And on the other hand, if you have such distribution, you can generate this distribution. Yes.
So the dyadic part is coming from the alphabet.
Yes, alphabet 2 and also like unbiased input.
Oh, okay.
Yeah.
So you get a prior on the input.
Yeah, that will change. Yes, yes. Let me like say a bit more about like this result. So if you have this distribution, how do you generate it? Well, you can use constant number of bits to choose which one of the mixture you generate. This is constant bits because I assume it's dyadic rational with constant denominator. And then once you fix the choice, it's like one of the 3 cases. You can use constant many bits to generate those distribution. Like for even and odd, you already see it. For the p-bias, because I assume p is also dyadic rational with constant denominator, like you can also do that. The hard part is to characterize, like you cannot do other cases. Okay, so before I go into the proofs, let me mention 2 open problems, including one is about the bound. Yes, so I said in our uniform symmetric classification, we need to assume n is sufficiently large with respect to d. And in fact, this sufficiently large is really crazy dependence. We need to assume n is a tower type dependence on d. And in case you don't know, tower is like 2 to the 2 to the 2 to the, like this is a crazy function, and the height is d. So it grows faster than any polynomial exponential function. Yeah, this is like a really bizarre dependence. However, for our proof technique, this is necessary. We use some graph theoretic results that tower type is inevitable. On the other hand, we don't think tower type is the correct answer. We think exponential function should be the correct answer, or at least some function that's reasonable, like exponential or double exponential or something like that. However, this is not, we cannot do that using our proof framework. And this problem is very meaningful because you can phrase it in other way. Like I know the 6 distribution are the ones you can generate using constant locality. But what if I just want this distribution? For example, I just want the distribution that is uniform over strings like of Hamming with 0 modulo 4. I know constant locality is not sufficient, but what is the locality needed, right? So using our results, you can rule out like log star and locality. But I don't think you can do that using log star locality actually. So improving the dependence here will improve the locality result there. And that's very meaningful question. Okay, so this is the first open problem. The second open problem is about dropping this uniformity constraint, talking about symmetric case. So this is a result we prove. Assume FU is exactly a symmetric distribution that can be generated with constant locality. Then FU is close to a dyadic mixture of evens, odds, and p-biased. And this close to is inevitable loss for an exponentially small distance. So even though the assumption is exact, like there is no distance, like there is no total variation error at all, the classification result we get is not exact. This is different from the uniform symmetric case, where we can say if you are exactly a uniform symmetric distribution, then you are exactly 1 over the 6. But here we don't get such result. You will lose some error inevitably. And the reason of this is we think a more general conjecture should be true. So if FU is exactly a symmetric distribution, then we think it should be exactly a dialectic mixture of some bitwise post-processing of constant number of independent evens and odds. So this is a little bit complicated, but I will show you an example that is not captured by our result, but captured by this result, by this conjecture. So here is an example. You sample independently x and y. X is going to be a uniform even string, and y is uniform odd string. And you take the bitwise end of it. So you can see this is one of the process that is valid by this conjecture. And if you look at this distribution itself, you will find that every bit is roughly 1 over 4 biased, because it's like uniform, and you take the end of it. However, there are some outliers. For even string, you will have slightly more probability outputting it. And for the odd string, you will have slightly less probability of outputting it. And this slightly is really negligible. It's like exponentially small. It's 2 to the minus n minus 1. So this is the distribution you can generate, which is a symmetric distribution, but the mixing weights are not dyadic rational of constant denominator. So this is not captured by our result. In fact, this shows why this error is inevitable in the statement I presented. However, this error can be eliminated assuming this conjecture. So we don't know how to handle such distribution. Okay, so these are the open problems and the results. And let me talk about proof. So I will show you how to rule out specific distributions. The first one is uniform over strings of exact Hamming weight n over 3. And the second is the majority, that is you output more ones than zeros. And then I will discuss the general case, like how you use those idea to get these 6 candidates. Okay, the first distribution is Hamming weight exactly n over 3. And because I presented you the results we have, we know this cannot be generated using local computation. But why? Why is that? And the key observation here is to explore this granularity issue. We are given unbiased coins. How can we produce a third? Right. So if you can generate this distribution, then by looking at each individual output bit, it needs to be a third biased, because this is like an expectation. However, the inputs are unbiased coins. So for example, assume this is one way to generate it, and we focus on B1. Say B1 depends on R1, R2, and R5. So there are 3 unbiased coins input, and we do some local computation, and output B1. Then the probability density of B1 should be an integer multiple of 1/8, because we only depend on 3 input bits, and each one of them is a half biased. And any integer multiple of 1/8 cannot approximate 1/3 very well. So even just reading, like just looking at this individual bit B1, we already see it cannot exactly generate this distribution. And this can be boosted. So for every output bit, we use this granularity issue to witness some constant distance from our target, and assume there are independent output bits, and there are k of them, then you will deviate more and more. In particular, this distance will be boosted from some constant to 1 minus exponential in k. And to get those independent output bits, we prove some structure lemma. This structure lemma says, after conditioning on some sublinear number of input bits, we can find linear number of independent output bits. So if we don't do conditioning, then it's possible that every output bit are correlated with each other, because some input bit may be like wired into every output bit. And in that way, we cannot find any we cannot find large k. But if you remove those highly influential input bits, you can find many independence. Yes.
Is this where you get to look
This is what, yes, this is where, yeah, this is major fact, yeah. However, for this version, we don't get tower type loss. What?
You're saying specifically for N/3 you don't get them.
Yeah, for N/3, we don't have exponential. We don't have tower. It will be exponential. Yeah. Okay, so assuming this, like given this structure lemma, we can execute this reasoning. So after the conditioning, we will see 1 minus exponentially small distance. Like, so this is a crazily large distance to our target distribution. And because we did this conditioning, so we need to union bound over all conditioning. And then the distance will be 1 minus 2 to the number of conditioned bits times like this exponentially small bound. In particular, this conditioning is sublinear, and the distance is linear. So this 2 to the little n times e to the minus omega n is still e to the minus omega n. It's still exponentially small. So the final distance is very large. It's like 1 minus exponential in minus n, far from the target distribution. So this argument shows you not only cannot generate this distribution exactly, you cannot even approximately like to 1 minus little 1 distance. Okay, so this is the first technique that we explore the granularity. And the second one will be about this majority distribution, that you want to output more ones than zeros, and why this distribution cannot be generated. And notice that here we don't have this granularity issue anymore, because the marginal bias is extremely close to a half, like it's not a third. And a half is generatable, because you are taking unbiased coins and you can easily produce a half. But then how do we argue about this? And the phenomenon we explore is the sharp cutoff in this distribution. Intuitively, FU, this output distribution, cannot generate strong correlation to produce a sharp cutoff between strings that has less Hamming, has at most n over 2 ones versus string with at least n over 2 ones. And to justify this intuition, we can go back to this structure lemma we proved. So after conditioning, we can find many independent output bits, and the Hamming weight is just summing over those bits, right? This is the Hamming weight, and because they are independent, the sum of independent bits by central limit theorem is going to converge to Gaussian distribution. And the Gaussian distribution has no sharp cutoff at this fixed Hamming weight n/2. So this is the intuition, or like the informal justification behind this intuition. However, there is a caveat here. The argument doesn't always work, because we can find independent output bits, but there are still like other bits correlating with these independent bits. So the total Hamming weight is not, it may not be Gaussian distribution. Like central limit theorem may not apply. In particular, here is an example. So assume like the first bit is x1, the second is negated x1, and then you output x2, negated x2, x3, negated x3, and so on. So there are like m output bits, and you output xi and negated xi simultaneously. So you can find many independent bits, because x1, x2, these are all independent. However, if you look at the total Hamming weight, it's always n/2. This is because you always output one bit and its negation. So it is the non-independence, like outside those independent bits, causing trouble. And the way to bypass this is to group them. So here, instead of just looking at x1, I will also look at the negated of x1. So we group them as a neighborhood. And we group x2 with its negation, x3 with its negation. So we have n/2 groups. And for each group, we realize that it's far from unbiased, because each group is always either 1, 0 or 0, 1. However, if we can output that distribution, if we can generate that distribution, not only every individual bit is going to be unbiased, but every 2 output bits needs to be unbiased. And in fact, for any constant number of output bits, it should be very close to unbiased, which is not here. So this is kind of like a bigger granularity issue, that after you do the grouping, you witness some deviation from your target distribution individually. Okay, so this inspired us to find like more general independence, not just about independence between bits, but also independence between groups. And in particular, we call it neighborhoods. It's like you fix an output bit, and you put all the output bit that is correlated with this one, and this will be the group. This is the neighborhood of this output bit. And luckily, we can upgrade our structure lemma, saying that after conditioning on sublinear number of input bits, we can find linear number of neighborhoods that are independent from each other. And this is where we lose this tower type dependence. And this is necessary. Okay, but ignoring those, and assuming this structure lemma, we can carry out the argument. So on the one hand, we view this neighborhood as just a larger output, like larger alphabet. And if those neighborhoods are not close to unbiased, which is supposed to be the distribution, if we can generate that distribution, then each neighborhood will witness some constant deviation from your target distribution. And because they are independent, you can use the same concentration argument as showing that it is 1 minus like exponential in minus n far from your target distribution. So this is one case. The other case will be assuming like most neighborhoods are actually close to unbiased, which is what you want for that for the target distribution. Then we can actually prove that the Hamming weight distribution satisfies central limit theorem, and it's going to be like Gaussian. This is because we not only have the independence between output bits, but we also like put in all the correlation that it can have. So the central limit theorem actually works here. And then because the Gaussian distribution cannot generate sharp cutoff, this Hamming weight distribution also cannot generate sharp cutoff, which means it cannot approximate well that distribution. So in either way, we win. So we witness some large distance in either way. Okay, so the general case will be like try to rule out any weird uniform symmetric distribution. And the like weird means like any phenomenon that you cannot see from Gaussian distribution. For example, maybe you include the Hamming weight of n over 2 to n over 2 plus root n, but you don't include the leading root n Hamming weight. So this is more like the majority case. Or maybe you single out the Hamming weight n over 2 and n over 2 plus 10, but skipping over all the Hamming weights in middle. Like Gaussian distribution will not do that. So any such kind of phenomenon will not happen, should not happen. And to do this, we designed a potential function h to witness those cutoffs. And in particular, this potential function will be evaluated roughly equals 1 for the claimed distribution that is weird. And for any Gaussian distribution, this weight function will have expectation close to 0, that is way smaller than 1. So the argument will be, we use the upgraded structure lemma to find many output neighborhoods that are independent. And then we divide into two cases. If many neighborhoods are far from the correct marginal, then we have granularity issue, which will produce a large distance by concentration. On the other hand, if most of them are actually correct, are actually close to the correct marginal, then we can analyze the weight distribution, which will be like Gaussian. And then we use this potential function to show that it cannot be the target distribution D. So this is like a win-win argument. And now let me finally remark that why does like even and odds will survive after this argument, right? Because for this for Gaussian distribution, it will also like be well, why it is special with respect to mod 2. And the reason is because we grouped things to talk about neighborhoods instead of individual bits. If it's actually individual bits, then those distribution, like even and odd, will not survive this argument as well. However, we grouped things. And after group things, this becomes possible. And the technical reason for this is this statement. Let X be some binary, be a p-biased distribution, where p is just from 0 to 1. And we consider the Hamming weight mod m, where m at least 2 is an integer. Then we need to understand the distribution of Hamming weight x mod m versus Hamming weight x plus 1 mod m. And crucially, they are the same distribution if and only if p is a half and m equals 2. So m equals 2 here will be like mod 2. And this statement doesn't work for mod 3, mod 4, and that rules out mod 3 and mod 4, and cannot rule out mod 2. And luckily, we can actually do mod 2, which is the local distribution I showed you. So this is like a key technical reason why we have these outliers from the argument here. Okay, so let me stop here and take questions. Thank you. Yeah.
Is it easy to say why in the structural lemma you need log star or power type?
So the structural lemma we prove is purely graph theoretical. So the statement in graph theory will be like this. You have left vertices and right vertices. Left vertices will be input bits, and right vertices will be output bits. And you connect to if there are dependence. So this is a dependence graph. And what we prove is you can remove like sublinear number of the left vertices and its connecting edges, such that there are many like linear number of right vertices that has like non-intersecting like neighborhoods, something like that. And the proof of this statement is to assume this doesn't work, like assume you don't have this statement, to remove the number of edges in rungs. So assume you don't have this, then intuitively you will have a kind of large heating set from the left vertices, a small set of left vertices that hits many right vertices. And after removing those, the total number of edges decrease by linear number. And you do this for many rounds. And every round you will lose a log. And the counterexample are constructed based on this argument. So the counterexample will be like kind of like a layered construction that reverse this argument. So yeah, so I get.
There's like a concrete graph.
Yes.
Example.
Yes.
All steps in your proof are actually hidden.
Yeah. Yes. And that counterexample is constructed based on this proof. Yeah. Yeah. I think that's a very good question. Yeah, I don't know on top of my hand, but yeah, this is a structure lemma, and we indeed use it to prove this classification and more and separating quantum and classical shallow circuit. So I think it's a fairly nice result, and yeah, yeah, I hope. I hope. Yeah, we can discuss afterwards. Yeah. Thank you.